I extend special welcome to our distinguished panelists, the moderator of this program, whose guidance and support have been instrumental in organizing this technical event. I also sincerely thank IA headquarters and the division board for their encouragement and approval of this CPD program. I am confident that today's deliberations will be intellectually stimulating and beneficial to all the participants. I once again welcome you all and wish the webinar a great success. Thank you. Now I am requesting Engineer Brahma Reddy sir to give brief introduction about the panelists as moderator one after one. Thank you.
Thank you, sir. Dr. Ram Mohan Garu. Good evening to all the respected dignitaries, eminent speakers, academicians, researchers, industry professionals, dear students, ladies and gentlemen. On behalf of the IEI Kothagudem Local Center, I warmly welcome everybody and especially the today's eminent speakers to this technical webinar on microwave imaging and applications, and not the least the King Sen from headquarters Department of Technical Department, and also the Secretary and Director General, and all other who are. I am unable to see the other dignitaries who are on the screen. Also, is convey my regards to them. Microwave imaging is an emerging and impactable area that combines usually electromagnetics, signal processing, and computational techniques to enable non-invasive sensing and imaging across diverse domains. From medical diagnosis to the security screening to ground penetrating radar through wall imaging and remote sensing and defense surveillance, microwave imaging is gaining increasingly relevance in both civilian and strategic applications. And I would like to bring now is a privilege to introduce the distinguished two panelists, Engineer Dr. E. Mallikarjun Erram-Setti Garu, Assistant Professor in the Department of Electronics and Communication Engineering at National Institute of Technology, Goa, who is specialized in microwave imaging, ground penetrating radar, and inverse problems. He holds a BTech in Electronics and Instrumentation from Kakatiya Institute of Technology and Science, Warangal. In the year 2007, both MTech Instrumentation and PhD in Microwave Imaging from the Indian Institute of Technology, Kanpur, in the years of 2009 and 2016, respectively. Dr. E. Mallikarjun research focuses on advanced electromagnetic imaging, including development of novel inversion methods and regularized iterative techniques for permittivity reconstruction. He has published multiple peer-reviewed articles in reputable international journals such as IEEE, IET, and Microwave and Optical Technology Letters and PACE and ETC. He has completed two research projects sponsored by SERP, Government of India, and Department of Science and Technology and Waste Management, Government of Goa. He holds one Indian patent on a robotic bionic prosthetic upper limb device. And about the other panelist, Dr. Arisha SB is also an assistant professor in the Department of Electronics and Telecommunication Engineering at Jawaharlal Nehru New College of Engineering, Shivamogga, Karnataka. That is affiliated to VTU of Belgavi, and he holds an MTech degree and completed PhD under the guidance of Dr. Mallikarjun Erram-Setti, the professor of NIT Goa in the area of microwave imaging. Dr. Arisha has over 20 years of teaching experience and 4 years of research experience, and has published 7 international journal papers and has presented research work at both international and national conferences. He is a member of professional bodies like IETE and ISTE, and has received recognition at the national level, including securing third prize in the E-Yatra robotics teacher competition at IIT Bombay. We, on behalf of the Kothagudam Legal Center and headquarters of Institution of Business India, sincerely thank both the panelists for joining us and contributing to the topic of microwave imaging and applications for the discussion and for the benefit of the participants. And
Thank
now,
you, sir.
to establish the technical foundation and other this thing, I request the panelist whoever has already loaded is the PPT. So kindly you can present this one. The questions will be put at the end of the both the speakers' speech is over. Thank you. Over to the panelist. I think engineer who is Arisha Garu is presenting first.
Sir, I
Yeah,
am presenting
Mallikarjun
first.
Garu. Okay, sir.
Yes.
Dr. Mallikarjun, sir, please, you can now present your presentation. Then the questions will be put at the end of it. Or you want me to ask a question and how you are going to present?
Sir, anything is fine, sir. For me, not a problem. So we will
I
do like
think
a
you
discussion.
present it. You present. Then I'll ask some question to few questions. Then open to the audience also.
It's fine, sir.
That
It's
will be
fine.
better.
It's
Okay.
fine,
Thank you,
sir.
sir. Please go ahead.
Yes, sir. Sir, thank you, sir. Thank you, Ramohan, sir, and Brahma Reddy, sir. Thank you for this opportunity. So let me start my presentation. Let me share my presentation slides. Sir, can you see? Can you see?
Yes,
Yeah,
yes.
yes.
Yeah. Okay. Um, good afternoon, everyone. Myself, Dr. Mallikarjun, and Assistant Professor in the Department of Electronics and Communication, NIT Goa. So, today our topic is microwave imaging and its application. So, it has divided into two parts. So, first part is related to the theoretical background and the formulation. So, that is going to be covered from my side, and the second part related to the numerical results and applications and future directions. So will be presented by Dr. Harisha SB. Yes. Okay. So this is a sessions. In these sessions, we are going to see first what I mean by a micro imaging, and what are its applications in the in our practical engineering, and then later we'll move on to see that what are the electrical properties of the material with respect to electromagnetic waves, and later we will see that electromagnetic scattering. So means like how these electric properties are related to the electric and magnetic fields. So then the formulation I will discuss this image reconstructions and tomography ground penetrating radar and future directions will be covered in the next presentation. Yes, okay. So this we have so many non-distracting methodologies are there, like a MRI scan and micro imaging, tera imaging, and infrared imaging, optical imaging, and X-ray imaging. So these all imaging categories comes under the non-destructive testing. Means we're going to find the property, means object properties or unknown object properties, or its a location or its a shape by not from means not invasive way. Okay, so from outside we try to, means the equipment is outside, it is not connected to the this object. From that we send a waves, electromagnetic waves, and we will receive the electromagnetic wave. So from analyzing that, so we are going to find its properties. Okay, so in the over the electromagnetic spectrum, so there are so these are the imaging models how developed. Okay, each one is having its own frequency range. So generally, this the current topic is a micro imaging. So it's falls. It means that frequency range of electromagnetic signal. It is like from 100 megahertz to in the tens of gigahertz. So these are the some of the imaging that you can see that we have ultrasound imaging. So this is in a sound imaging. So there the frequency is generally will be used for 10 to 2 to 10 megahertz of audio signal, that is audio signals means they send. Okay, so in that, so that we can see in our all hospitals, so they will use this ultrasound imaging. So the picture shows that is abdomen scanning of any pregnant lady. So the main problem with respect to this one is that it is that the resolution is very poor in ultrasound imaging. But main advantage is that it is a non-ionizing effect, means that there is no harm to our human body. The second imaging, you can see this MRI imaging. So the MRI imaging, the frequency of electromagnetic signal is around some 10 to 100 megahertz. The main advantage with respect to imaging this MRI is that that you can see the object that inside that very clearly, and compared to this ultrasound imaging, we can get a very good picture. But the main problem is that so it requires that it's a that the cost of the equipment is a little more high in case of the MRI imaging. So the next imaging that we have seen here, that is X-ray imaging. So where the frequency range is around some 30 petahertz to 30 gigahertz. So this one, if you see that um, the main that X-ray imaging, they can it's a means we try to get using the density, like a bones are having a more density, so that the absorption of the X-rays are more. So from that, if you plot is a density profile, so we can able to see the inside. But the main problem is about this X-ray imaging. It's a ionizing effect, means it's a okay. It is a okay. It's a harmful for the human body if it is exposed for the longer duration. Next one, we can see this imaging, like in a thermal imaging. So we call as IR imaging. So it's a and so it is like in a surface imaging. Like so here that the temperature mapping, we will try to map the temperature. So from the temperature profile, we can able to see that that object that okay that outer properties. But this but in the thermal imaging, we cannot see that that the object properties inside the body. Okay, so this is like an only surface imaging. So now comes to this. So this is a some of the comparison table that whatever we have, that CT imaging and MRI and ultrasound and the microwave. So when it comes to the microwave, that so first one is a non-ionizing. Microwave does not create any ionizing effect on our human body. Second one, we will get a resolution, a quite moderate resolution we will get. And when it comes to the cost, it's a low cost. And portability means that the device size is also is small, so that we can use it in any field applications. So let's come to what is mean by microwave signal, microwave imaging. So in the microwave means, then we will use a electromagnetic signal with the range of, so in the megahertz to gigahertz. Generally, we will use around that middle frequency is around 1 gigahertz. So 1 gigahertz, that frequency means it could be 1 gigahertz or 2 gigahertz. So, but that's the middle frequency we will use. So we will use the transmitter. So the electromagnetic signal will be transmitted. So like this, you can see here. So this is called the transmitting. So, and it will send the electromagnetic waves through the antennas. Then it will interact with respect to object. So now here we have the object that we are interested to find out. Now that object undergoes scattering and it will deliver the scattered field. So it will deliver the scattered field. So this E field and H field will come. So now this E and H field will be measured by the receiving antennas. So here also we will use the receiver is antenna only. So from that we will do the data processing. So we will use some of the algorithms over the received electromagnetic field, and we'll try to find the image. So this is like an active imaging system. So in the active imaging system, we require one transmitter, transmitting and receiving. So this transmitting and the receivers are the antennas. So which works in the frequency range of around, so like around 1 gigahertz. So generally that we can say for all applications, so that micro we will use 100 megahertz to 10 gigahertz. So this is a frequency based on the applications. So we will select the frequency. Now, okay. So here in the micro imaging, so this comes under the class of the inverse problem. It comes under the class of the inverse problem. I will just briefly discuss the inverse problem. Like let's say that uh, in a forward problem, so we know we have the objects, like we have the object. So the object could be like any object you get, it is having some epsilon or it's having mu r. So these are the permittivity of an object, that is electrical permittivity. I will discuss later what is meant by permittivity and is a permeability. So now what we do in the forward problem, so we will send the incident field, that is incident electromagnetic field, that is we call E incident. Then from this, then we will get a scattered field. So this is kind of the scattered field. Here's a scattered field. Scattered field. These are comes under scattered field. So now, in this case, from the incident field and from, okay, this is the operator, that is we will use in a like an electromagnetic scattering field operator. So we try to find the scattered field. So here the unknowns are the scattered fields. Unknowns are the scattered fields. Object properties are known. Input electromagnetics are magnetic fields are known, and we have the operators, like in a, how the scattering operators are there. So that also we know. And the unknown is the scattered field that we are going to find out. But in the inverse problem, we know the scattered field. So we know the scattered field. These are the scattered field. And we know the operator. We know the operator. So inverse problem observed operator. So it means that this one. So here is a scattered field. Scattered field. Here the scattered fields. And operator we know. And the estimate here we try to find out the what is the permittivity, what is the permeability of the object. Okay, this comes under the inverse problem. So this all micro imaging problems comes under the class of the inverse problem. So generally the forward and inverse problem defined by which problem easy to solve, then we can say is a forward problem. Which problem is difficult to solve can be comes under the inverse problem. Okay, for example, you can say that suppose if if you are given one charge q1, other charge is q2, and if the distance we know, try to find the force, try to find the attraction force or the repulsion force from this. So we can find from the Coulomb's law. So finding in a force from the two charges and with the given distance, and you know the background medium, then this comes under the forward problem. Whereas inverse problem, we know the force, we know the force, we know the distance. If I ask you to find the what are the charges, so what are the values of the charges, then it is comes under the inverse problem, because finding any charges is a bit difficulty. So but finding any force, then it is become easy. Okay, so the easy problems comes under the forward problem, whereas in a difficult problems comes under the inverse problem. Okay. So this micro imaging is having many applications in the field of medical imaging, in the field of geoscientific exploration, and in the field of structural monitoring, and in the field of the security applications. So let us see that. So this is about the biomedical field. So especially in the breast cancer imaging. So far we have X-ray mammography is there. So through X-ray mammography, we used to find the breast cancer, but the accuracy of the breast cancer is limited to only to the 50%. But whereas if you use microwave imaging, through microwave imaging, we can able to identify that the cancer tumors in the breast. Okay, so how we will do that? So the cancerous tissues is having higher water content. So here it is having a higher water content. By finding that higher water content leads to the higher permittivity and the conductivity value. By measuring this permittivity and the conductivity value, so we can able to identify that cancerous tissues. Okay, so now there is only one imaging technique in the entire discussion of all other imaging techniques. In that, microwave imaging only able to give the electrical parameters of the dielectric and conducting objects. No other no other imaging model can give you the dielectric and conducting properties of the dielectric objects. So through these techniques, so we can able to apply into various fields. So this is about this related to the breast cancer. Next we will see, we also can apply brain stroke imaging. So where the dielectric properties of the brain tissues varies based on the type of problem. Like you see ischemic stroke is there is a reduced water content. So because of the low permittivity value. So by if you when you are using in a brain imaging, so if permittivity values are coming low, then you can that there is a problem. This is related to ischemic stroke. Then there is a hemorrhage stroke, where if there is any blood present, so in the brain, the dielectric properties increases. So by measuring these dielectric properties, if it is come beyond the normal limit, so we can say that so there is a problem that might related to hemorrhage stroke. And also we can use that bone and lung image. Suppose if there is any fractures are there or any density variation or any some tumors are available. So within our bone structure can also be detected through microwave imaging. So these are the some of the applications are there through basically these are the ground penetrating radar. So here also we will use the micro imaging. So it is having numerous applications are there. Yes, sir. Here numerous applications are there. Like one is that soil characterization. So this is so by doing the soil characterization, we can measure the water content in the soil or any some special type of minerals are present. So that also can be detected using this one. And forensic application, suppose if any dead body is buried, so you wanted to find out any buried objects. So that also can be detected through this GPR technology. And any landmine detection and archaeological survey and security through the wall imaging and planetary exploration. So in any like any mission that we are sending to in other planetary, so that orbit always will have GPR technology. So where that this technology, okay, using this technology, they use it to analyze the what is the soil characteristics over there. So the glacier application, so this is can be used to finding the depth of the ice level in various regions. And the road survey, if road is having any cracks or anything or in any bridges, so this technology can also be used. So for detection of the underground pipes also can be done. Okay, so it is having in a many application. Even there are many companies. So in a commercial available companies are there. They are producing this GPR machines. So where we can direct, it's a portable machines. So we can directly use in any applications. So, so these are some of the security applications that, okay, in any airport they are using this. So detect any metal objects. So X-rays also they use, but in X-rays is little is more harmful for a human body. So generally they are working on try to deploy in other type of technology. So this is also one that okay by using wanted to find any cracks so within our any wall, okay, without breaking it, and by finding the crack, then we come to know that what is the durability of that wall, and if it is okay, if the wall can sustain, or if it is having any more cracks, then okay, then it won't come for very long duration. So these are the okay. So these are the some of the applications of the micro imaging. So now I will just go through the properties of the material. What is the dielectric and okay properties or magnetic properties. Okay. Then how it related to the electric and magnetic field. Then I will discuss first. Okay. So this is the dielectric properties of any material that okay it shows to the ability of it store the electric field. So this okay. So we have the free space permittivity. So because of that is epsilon naught, so it's a free space permeability in most of our material. So we don't write that with respect to okay absolute permittivity. So we will always represent the material permittivity as relative permittivity. So this, if you wanted to find the absolute permittivity value, just to multiply with respect to the free space permittivity. So most of the material which is our practical use or our environment which is having in the range of 1 to 80. So these are the relative permittivity values. So which are okay okay, which most of the material that we wanted to test it, so it comes under this range. So these are the okay. So it will so that the slide you tell you that the relative permittivity values of different of material. So we can see some of the one like you see soil. Okay, generally it's a dry soil. It's around 3. But if it is having any water content, then this permittivity value increases. And you can also see the water. Okay, so if the water is having the conductivity, then it's not conductivity. It's a dielectric constant is around 81. Okay, so then there are other general materials are there like an amber and any glass. So most of the things are coming from just 2 to 3. So these are the most of the material comes from 2 to 3, 2 to 8. But there are some special materials are there that means that permittivity values are too high. So if you see, this is a magnetic material. So this also same this one. So one is related to the electric field. So other related to the magnetic field. So here also the same thing that whenever that these are the uh, okay. So the permeability. So this concept will tell you the okay ability of the material okay to polarize. So how the dipole moments are there, how the dipole moments are aligned with respect to the external magnetic field. Okay, so if more dipole moments are formed when you apply the external magnetic field, then we can say that it is having a high relative permeability. If dipole moment are small, then we can say that okay. So then we can say that the relative permeability is very small. Okay, just you can see the picture. So before applying any any magnetic field. Okay, so this magnetic field I'm applying 0. So okay, before applying any magnetic field, the dipole moments. So these are the dipole moments are located very randomly. Okay, so but whenever the moment you apply this magnetic field, then this all dipoles are oriented in along the magnetic field. You can see here along this one. So if you add all together, then it will form a total a dipole moment. Okay, so now if the dipole moment is larger, then we can say that then that material is having the larger permeability value. Okay, so this is a free phase permittivity, that permeability. So this is a mu naught. So that then we have the absolute permittivity of the medium. If at all wanted to find out the mu of any material, just you simply need to multiply with respect to the relative permeability. So, but in most of our common material, so
నేను జూమ్ లో ఉందా మొబైల్
all are mostly equal to 1.
అయిపోయినా కాల్
Okay.
చేస్తాను
In
సరే
most of the material which we are interested to find the properties, all are having the relative permittivity almost equal to 1. So in the micro imaging, so we mostly concentrate on try to find what is the epsilon r. So this is the one more property that is called a conductivity. So if the medium is having any okay any free electrons, okay, then that can be characterized by this. So the conductivity. So in our all microimaging, so we are interested to find out what is the epsilon r value, what is the mu r, what is the conductivity value. But the mu r value generally it almost equal to 1. So in our microimaging, okay, we are interested to find the epsilon and sigma values. So now, okay, so this is some of the basics about this of our how our this electromagnetics, how our this electric properties or magnetic properties are related to electromagnetic wave can be given by Maxwell's equations. Okay, so we have the four Maxwell's equations. So Maxwell's equations one, okay, so Maxwell's equation two and three and four, three and four. If you see here, uh, okay, so B, so whatever the B is there, so we can write as mu into H, mu into H. Okay, so we can write as mu into H. So, so E means is an electric field, H is equal to magnetic field, and mu is equal to the permeability value of a material. Okay, and similarly, the permittivity related coming from this side. Okay, so D is equal to epsilon into E. Okay, so now, so the second equation from the Ampere law will tell you that how permittivity value is related to your magnetic field as well as the electric field. And there are one more is there. Suppose in case if any the free charge is there, so this is a free charge. So if there's any free charge is there, then how we related to the electric field, where here D is equal to epsilon into E and B is equal to mu into H. Okay, if you substitute this, then we come to know the relation between electric and magnetic field with respect to epsilon and mu. So now, what we need to do, we need to find out what is a electric field equation, what is a magnetic field equation. Okay, so so we will use these four equations and we try to find the relation. Okay, so now if you see that Maxwell's equation, that previous equation will tell you with respect to time domain. So now this one will tell you the with respect to the frequency domain, where the time domain is representing the time domain derivative. If you remove it, so we can represent with respect to the frequency domain. So this equation, the four equation with respect to the frequency domain, and it is represented by using this formula. Let's see here. So this also somehow again is we this slide will tell you that solution to the electric field. So now if you see the first equation, so this is my first equation, this is my second equation. Okay, so if you see the first equation, so this first equations contains only the electric field. So you see electric field and the electric field, and this mu and epsilon is any dielectric properties of a medium. Then so J is equal to the so this mu, so this is not there, only this is there. J is equal to the current density. Similarly, the second equations, you can see that it's with respect to the only the magnetic field. Okay, only the magnetic field, and it will with respect to the current density. So if you write it in a further further if you simplify it from this, so we are going to get the first equation. So this is my first equation. Again, this is my this third and this is the fourth. So this third and fourth equations will tell you this so electric field equation, and the fourth equation is the magnetic field equation. So where is the wave number? Okay, let's see the next. So if you further make it, if you further simplify it, then we'll get the integral form like this. Okay, so this is my electric field equation, this is a magnetic field equation, and this one is coming to a green function. So using these two equations and the green functions, so we need to estimate the properties of a dielectric medium. Okay, so we will see that. So before going to that, so I'm just going to just discuss it. That is what will happen in the electromagnetic scenario. Okay, so let us say, so this is my object. So this is my object. So this is my any unknown object. So this is my object. So it is having its own relative permittivity and it's having its own relative permeability. And this is placed in our free space. Okay, this is a free space medium, epsilon naught and the mu naught. So whenever the electromagnetic wave, that is electric wave is coming, so this is an electric field E incident. So we call as incident wave. Whenever electromagnetic wave and it is interacting with the medium, then the scattered fields are generated. So whenever it is interacting the medium, so it will generate the scattered fields. It will generate the scattered fields. So now that scattered fields, okay. So now the equivalently what we do, so we will represent that entire dielectric object using one equivalent sources. Okay, so this E epsilon r and mu r related to are represented by the equivalent sources. So this is a dielectric equivalence principle. So we are representing the permittivity and the permeability values with respect to the equivalent sources. Okay, so now you can see here now. So that so in any point, if you see, this is called a total field, the total field, and this is called my incident field. So this is a scattered field. This is scattered field. So it means that suppose in any point I wanted to find the field at this particular point. So now there is a two fields are coming. One is the incident field present, also the scattered field present. If there is no object present, then there won't be any scattered fields. Because of the object, both field present. One is an instant field, one is a scattered field. That's what I have written. So E is equal to E instant field and the scattered field. Now the scattered field equation is given by j omega mu integral. This is a green function. This is operator, and this we know. This is a green functions. Green function, and this is a equivalent source. This is a equivalent source like this. Okay. So this is required in formulating the formulating the micro imaging problem. So now this is a case when it comes to the, so previous case is related to the dielectric objects, whereas in this case is come to the conducting objects. So conducting objects in the sense PEC, perfect electric conductor, or any metallic objects. So in the metallic object, the electromagnetic fields won't penetrate inside. So what will happen? So it will come like this, and from that only it is reflected back. So it will come like this instant field, and it will be reflected back. Okay, so because of that, so it won't go inside. So the equivalent problem will say like this. So the whatever the equivalent sources, that will present only on the boundary. So it will not present on the inside the metallic objects. Okay, suppose let us say we have any problem that, so this is a metallic objects. So within that some other object is there. I wanted to find this object within the metallic objects. This is my PEC. And within the metallic objects, I wanted to find this object. Through micro imaging, it is not possible. Why? Because whenever the PEC present, the electromagnetic wave will come and it will reflect back. So it won't go penetrate inside. So it unable to see. Okay. So now, okay, come to this. So this is a kind of a setup we will use for micro imaging. So we have many applications are there. So based upon the applications, so we will use different type of configuration. So first one is a tomographic application. So where we will do, uh, so here, so this is my object. So here is my object. Here is my object. So in the what we do, first we will illuminate, or we will send one electromagnetic signal through like this. Electromagnetic signal, then what will happen? So it will scatter in all the fields. So the scattered will come in all the fields. Okay, it will scatter like this in all the direction will come. So now what we need to do, so we need to measure these scattered fields around the objects. So in that particular case, what we do, so we'll keep the receiving antennas around the objects. Now you can see this is this one as a receiving antennas. Okay, so it will keep around the object. So now, so let us say if one transmitter is there, let's say one transmitter, one TX. So we need to find the entire scattered field. So we will use a finite number of the receivers. Let us say 30 receivers we are using, 30 RX. Okay. So in one transmitter, one transmitting field, so we are going to get 30 measurement fields. Okay. So now the transmitting wave is coming from this angle. But now again, but we need more information about the object. So what we will do, so we will send the again the incident field from in other direction. So from this direction again we will send again whatever the scattered fields are coming, so we will collect from in other places. Okay, so like that this process will be repeated throughout, okay, 360 degrees. Okay, so now one transmitter one, so I measured 30 fields. So in the next direction I will send a incident field from in other direction. So that time also I will measure 30 fields. If I do like this, again 30. So if this process is repeated, if the process is repeated for 30 directions, then we have the total number of the fields are 30 into 30. 30 into 30. So this is what we will use even in our MRI scanning. Also, you can see that when patient is lies inside it, so there is a one very big, okay, equipment is there, but inside equipment we cannot see. But generally the process is same. So you are suppose you wanted to do the MRI scanning, okay, of your head. So your head will be illuminated from all different of directions. Okay, and it will eliminate the fields, and the fields also will be measured in all the directions. So from that they try to estimate the your complete head profile. So similarly in microimaging also it is like that. Okay, so we need to eliminate the object in all possible angles, and whatever the scattered fields are coming, that also you need to measure in all possible angles, so that you will have a considerable amount of the measurements. Okay, so this we will use this kind of configuration will use in a tomographic applications. So whenever the GPR, that is ground penetrating radar, because our accessing region is limited, because if the, okay, because we cannot keep the antennas inside the soil. Okay, we can only keep the antennas above the subsurface. That's what is, you see, all the antennas are kept in above the subsurface, so that we cannot keep the inside, so we cannot eliminate this object. So this is my buried object, so this is my earth subsurface, this is earth subsurface. So now, so we will send the, okay, measurement incident field like this only. So we cannot keep the antenna inside the soil. So in that case, we can say that, so this is a full space region. So this one we call as a full space measurement. But whereas this case we can the half space measurement, means we can have only the half region. So we cannot have the access of the other region. So generally these two configurations we will use for in a micro imaging applications. Okay, but now let's say this one, but how many measurements we need to take it? So how many measurements we need to take it? Because let's say if I'm incident from like this, so I need to get the scattered field measurements around like this. But how many are possible in the around it? Around infinity number of the measurements are possible. But in general, the micro imaging theory says that you no need to measure the end in the, okay, many directions. No need to measure the scattered field in many directions. You can, okay, you can measure the fields in only specific direction with a specific number. Okay, that number is sufficient to get the maximum information of the object. If you measure more than it, then it will be the redundant only. There is, you cannot improve the results. Okay, so according to this formula, so we have some formulas are there that, so this formula we will use. So let us say if this, let's say this is my object. The object is fitted in a one kind of a square. So you fit the square. So now you measure this distance. So this distance is equal to, let's say diagonal distance is equal to 2a. 2a. Now you need to follow this principle. The total number of the measurement is equal to, so 2 into gamma is equal to some fixed number. We can generally we can say 1. 2b is equal to, that is a background propagation, 2 pi by lambda. Then this rs is equal to this one. Rs is equal to, let's say it's a 2 into a. So from that we need to measure it. So now you calculate it, whatever the n value you are getting, so those number of the measurement value we need to take it. Suppose if n is equal to 12, if n is equal to 12 is coming, then you have to keep the receiving antennas 12. Okay, suppose if I increase the n is equal to even 20, but your results won't get improved. Your computational complexity increase if you have the more number of the measurements. Okay, so from this, so this one, these are the some of the antennas we require. That is, we will use that because in antennas plays a major role in for transmitting in a signal as well as receiving in a signal. So we will use a broadband antennas. So it will have a very wide frequency range. Okay, so it means that based upon the applications, let's say if you wanted to use for a ground penetrating radar, that is a GPR application. So in the GPR applications, we will use the antennas in the range of the megahertz. Maybe it could be the 700 megahertz to 700 megahertz to, let's say, 3 gigahertz antennas we'll use. Okay. Sometime what will happen? We need to use this, okay, we need to collect the information from at different of frequencies. Okay, it means that, so you are doing the process, that measurement process you are going to do at 700 megahertz, 800 megahertz, like that, with a different frequencies we'll measure. From that we'll try to get the objective properties. So to have that, okay, to have the provision to measure the scattered field at various frequency range, so we need to have at a wide frequency coverage. The antenna should able to supply wide frequency coverage. Okay, then it should be the have the high directivity. Okay, the directivity of the antenna also should be it should be the focused one. Okay, so it's not like that it will send the energy in all the directions. It should be the focus where object is located, so that object must be covered within that. And it should have the compact design, because we wanted to make that equipment should be very small, then it should have the compact design. Then the some of the applications require biocompatible material first. Okay, for human interfacing applications. So some of the antennas we will use as some Vivaldi antennas and horn antennas and patch antennas and monopole antennas. Okay, so based upon our application type, we will use different type antennas. Okay, so these are the some of the measuring techniques. So in our practical application, so the measurement setup consisting of, so in all electromagnetic fields can be measured through only vector network analyzer. So this is a VNA. So VNA. So through VNA, vector network analyzer, through VNA, we try to find the S parameters. So from the S parameter, we used to calculate the measured scattered fields. So what will happen? So here is antennas are there. The antennas are located. The antennas are positioned like this. Antennas are positioned like this. So now, so what happened? So but generally in our practical applications or in our measurement domain, so what we do, so the antennas, sometimes we will use only the two antennas. Okay, the two antennas we will use, one is a transmitting and one is a receiving antenna. Then what happened? So whenever the transmitting antenna is working, the receiving antenna should move like this, different of location. Receiving antenna one, it has to measure here. Now the receiving antenna alone can move to next location and measure here, and it goes to the next location. It goes to here, it goes to here, it goes to here. For that, what we do, we need that, okay, motorized control will be there. The motions of an antenna, the motorized control will be attached, so that the receiving antenna can move at various locations or various directions. Instead of using many antennas, so you can use only one antenna, two antenna setup. Now when transmitter is sending, the receiver will move all the directions like this. Okay, but it's a time consuming process, but it will do. Next, what will happen? So in the TX, now it will move TX also. We will use another motor setup. Now the TX also will move to some other location. Again, the process is repeated. So that's what we will use the any motorized control. So next one is that so this antennas, okay, switching network. Okay, so if you use this, okay, this is a setup. If you use only two antennas case, the switching network is not required. But if you use the more number of the antennas and you wanted to do the measurement very fast, then we require the switching network. The vector network wise is having the two outputs. One is connected to the TX, one is connected to the RX. But now, which antenna should connected to the TX terminal, which antenna to be connected to the RX terminal. So that is decided by the switching network. Okay. So now through this one is a VNA part, one is a switching network and antenna, and motion control unit. If these things are there, so we can able to find out the S parameter in each measurement. So from the S parameter, using the calibration network, so we can directly find the scattered fields. So like that, the process continue. So the problem formulation. So now, uh, we have the scattered fields, we have the incident field. Now we need to find out like this. You cannot. So this is, you see this one. So these are the two equations. So that are available. So one is a scattered field equation, one is a total field equation. So now, so these are the unknowns. So which one is this is my unknowns. This is a permeability, related to permittivity. That is a chi is equal to epsilon r minus 1. Okay. So now, so this is a known, this is a known, this is a known, and this one is this is a green function also known. If you know the background media, we know the green function. Only unknown things are like this. So this is unknown, that is a contrast value that related to the related to permittivity of an object, and this is also unknown. So this is unknown. So this also unknown. This also unknown. So you see, these are the known values. These are the unknown values. So from the known values, we need to find the unknown values. Let's see here. So I can make it in a matrix form. I can matrix a matrix form like this. So U is equal to U incident GD and U cow. This from the first equation it is coming. This is from the second equation. So now my interest is only to find out this chi value. Let us see if I able to find out the chi value through this equation, then what will happen? So let's see this one. So U scat is equal to GS. So that U also unknown. So let me find out from the first equation, then what will happen? So if you find, so if I do that, then what happen? This one U, so you make it to this side. So it will come I minus GD into chi, This is a U is equal to E incident. Sorry, U incident. So if I find the U, then I will get, so U incident divided by I minus GD into chi. Now what you do, you substitute the U value in this equation. You substitute here. Then the E scat is equal to U incident into chi divided by, so I will get like this, I minus GD into chi. So this is my equation complete. But you see, the unknown is appearing in the numerator as well as the unknown is appearing in the denominator. So the unknown is appearing the both. So because of that, so we call this problem as nonlinear problem. Okay. So we need to use proper optimization techniques to find out this chi value. Okay. So it is a nonlinear problem. So microimaging problems are nonlinear. That is the first one, nonlinear, where unknowns are appearing numerator and the denominator. So because of that, so the problem become nonlinear and we need to use the suitable optimization techniques to find out this chi value. And the second one, this one, you see, we can make it to linear provided this magnitude is very small. This is small. If you neglect it, it's a very small, then we can find out this equation. So what we do, if you see this one using the Born approximation, you can write like this. So if the denominator is neglected, so we can say that, so this is a one kind of an optimization problem. Okay, but it's an approximated one. So this scatter field is known, GS is known, E incident is known, and chi is unknown. So what we do, this but looks like it's a simple equation, but it's not a simple. But this problem itself, it is also having this. These are ill-posed problem, means ill-posed and ill-conditioned. Okay, ill-posed and ill-conditioned problem. Ill-conditioned problem. It means that, so the matrix, okay, we cannot inverse directly. Okay, if I write like this in a matrix form, I cannot find so you can same equation I am representing as a linear equation. I cannot directly find the E inverse because A is not a square matrix. Even if it is a square also, we cannot inverse directly, because that will get a very wrong values. Okay, so that what we do for that, what we do, we will use this some kind of a regularization. Okay, so since all micro imaging problems are non-linear and ill-conditioned problem, so because of that, we will use the regularization techniques. Okay, to solve these one, we need to use, we need to use, we need to use regularization techniques, regularization techniques, regularization techniques. Through regularization techniques, so we are going to get the object permittivity or object any shape and locations. So okay, so just I discussed it how the measurements can take in place. So once the measurements are taken place, so we need to do the modeling. So once the modeling is done, then we will use the suitable algorithms to find out the this unknown parameters. Okay, so in all micro imaging, so we are interested, basically we are interested, one is what, the first one is the object identification. Object identification means whether object is present or not, it is present or not. Let's say if it is a present, what is its a location, what is a location of an object, location of object. Then once a location is found, then what is the shape of an object? Shape of the object. So once shape is found, then we are interested to find its electrical parameter. What is epsilon r? What is a sigma? What is a mu r? So in all micro imaging, so we are focusing on these four things. One is object identification, whether object is present or not. Second one is if it is a present, what is the location? And if it is a location, what is its a shape? Then once you find the shapes, then based upon application, we can able to find this permittivity values. Okay, so this one I will okay, I conclude that only this mathematical, okay, just a brief in, because the short time, so it is a background, there are so many mathematicals are involved, so I have not covered it, but it is a very big chapter. But I just wanted to touch what are the major applications of the micro imaging, then what are the okay electrical properties of a material, then how it related to the electric field and the magnetic field, then then in the micro imaging what type of setup we will use, from the setup how we are going to calculate, how we are going to formulate the problem. So up to that I covered it. So next presentation, so Ms. Dr. Harisha will tell you about the that application of the algorithms to to find this object location, shape, and the permittivity values in the next presentation. So these are the some of the references. If anyone is interested, they can get. So very good book is there, that micro imaging by Pastorino. Like that, many good references are there, but some of the references I quoted. So thank you, everyone.
Thank you, sir, for the nice presentation.
Thank you, sir.
You have explained the basic principles of microwave engineering, especially the role of electromagnetic wave interaction, scattering mechanism, and inverse problem formulation. And really, it was really a manner very accessible to the students and practitioners also. But one thing is, I would like to ask you to throw some light. How does this microwave imaging differ from magnetic resonance imaging?
Sir, actually, that actually the operation itself is difficult, sir. Where we will use that like magnetic resonance imaging, like actually it related to the that they should have some kind of a molecules. Okay, I'm not into the technical side of the magnetic resonance imaging, but what will happen? First, you keep the that this our biological body at very high magnetics. Okay, they will send some kind of an very high magnetic field, then our body particle will excite. So from that again they will send some kind of an electric pulse, then with that it will radiate it. So you see there it requires very high magnetic field. But in our micro imaging, so you don't require any high magnetic fields. Okay, we don't require any kind of our particle to resonate it. Okay, so here what we do is a simple operation. You send a electromagnetic signal, then automatically the material definitely it will scatter it. Your objective is only to find the scattered fields with the same frequency. Suppose if I send a frequency of the 1 gigahertz, the scattered field also at the 1 gigahertz. So here it does not require any high magnetic resonating. That resonance should not be there here.
Thank you, sir. Thank you, sir. Anybody? I think general audience, I think will love after the talk by the Mr. Dr. Harsh.
Yes, sir. Yes, sir. We are.
Yeah. I request Dr. Harisha to kindly present his.
Okay,
So I'm
Thank you, sir.
closing now.
Sir, can you see my
Yes, I
slides?
can see you.
Yeah,
Yes, we can see you.
visible.
Okay. So, good evening, sir. So, first of all, I would like to thank the Ram Mohan sir and Brahma Reddy sir and Shrikant sir and Mallikarjun sir for giving me an opportunity to present in this webinar. So, Mallikarjun sir has already started. So, already explained what is microwave imaging. So, I will quickly go through the introduction part. Already sir explained. So I start from here, sir, a little bit. So like many modern technologies, microwave imaging also has a deep historical roots, starting from ancient optics and evolving through the centuries of scientific breakthroughs into today's advanced imaging system. So it started in the ancient foundations that imaging studies began with human vision and light perception. The Greek scholar like Euclid and Heron studied reflection, refraction, and mirrors. And then in 1021 AD, Alhazen introduced the idea of eye as a passive receiver and explained the image formation. Then wave theory of light came. There were Christian Huygens proposed the wave nature of light. So challenging Newton's corpusculus theory. And the Thomas Young's double slit experiment confirmed the wave behavior. So earlier the imaging means through light, but now the light is also wave. So is it possible to do the imaging through other frequencies also? So then the work by Ampere, Faraday, Gauss, and Weber led to Maxwell equation describing the electromagnetic wave propagation. And Heinrich Hertz experimentally confirmed electromagnetic waves travel at light speed, so enabling non-optical imaging also. So imaging means not only the light, so other electromagnetic waves also can be used for imaging. And then in 1970s, digital imaging emergence and microwave radiometry demonstrated by Nobel laureates Rayl and Hevish, and synthetic aperture radar techniques adopted for airborne and spaceborne imaging. So, and in 21st century, advance in semiconductor and signal processing expanded microwave imaging applications. Now it is widely used in security screening, medical diagnostics, and subsurface exploration. So this is a little bit history of the microwave imaging. So in microwave imaging, there are two types of microwave imaging are there. One is qualitative methods and quantitative methods. So qualitative methods, they provide only the morphological features such as shape, size, and location of the scatterer or object. Whereas quantitative methods, they provide the electrical properties of the object also. So along with the morphological features, electrical properties are also provided by the quantitative methods. So qualitative and quantitative methods are the two reconstruction methods in microwave imaging. So these methods are ill-posed and non-linear in nature, as sir said. So ill-posed means it will not satisfy one of the three conditions like existence of solution, uniqueness of solution, and stability. So whenever there is a change in the input, output should also correspondingly change. So there should be a stability with a relationship between the input and output. So if one of these are not satisfied, then it is ill-posed. And this non-linear comes because of the multiple scattering effect. So the scattered wave once again recursively interact with the object and its surroundings, so that because of this multiple scattering effect, the nonlinearity arises. And also in this qualitative and quantitative method, the local minima problem, when we are finding the solution, they struck at the local minima, we cannot get the solution. And these methods are iterative methods. So high computational time is required for these things. So because of these disadvantages, so we can have an objective to solve non-linear ill-posed problems of quantitative microimaging for dielectric objects. So in the dielectric objects, the permittivity we will find. So we can solve non-linear ill-posed problems of quantitative microimaging for dielectric objects. So we can keep first our objective is like this. And so again, there are linear and non-linear approaches are there to find the micro reconstruction. So in that linear approach, one of the method is Born approximation method. As I sir told, the Born approximation method assumes the scatterer is weak. So it assumes that scatterer is weak, so scattered field is neglected. So it assumes the total field is equals to incident field. It approximates like that. So the linear approaches, they will do some assumptions. Okay, so not only Born approximation methods, various methods are there. They will assume some they will approximate something, or they assume something. So the Born approximation, it assumes that the scatterer is weak. So these these are as they approximate, so linear, and they are quick and reliable in reconstruction, but they are ill-posed but linear problem. But as they are ill-posed, direct inversion of ill-posed equation produces the erroneous results. So because of this, we should use regularization techniques. So the regularization techniques are useful in controlling the ill-posedness and provides the stable solution. So some of the regularization techniques are truncated singular value decomposition method. So in truncated singular value decomposition method, so after finding the SVD, so singular values below certain tolerance are truncated. The singular values with the small value are truncated because they are by the noise. And finding here, the challenge is finding the correct value of tolerance is the challenging task. And another regularization method is Tikhonov regularization. In Tikhonov regularization, replace ill-posed problem with well-posed problem by introducing a regularization parameter lambda. So here the regularization parameter lambda is important in the Tikhonov regularization, but here the challenging is choosing the correct value of regularization parameter. For this also, again, there are some techniques are there. So in the linear problem also, so the regularization is important, and these linear approaches will not assume they will as they do assumption, they will not consider the nonlinear effects. So the linear effects, as they not consider the effect of multiple scattering, that is nonlinearity. So in the reconstructed image, there are some artifacts are there. In the reconstruction, there are some artifacts. So an iterative approach we should develop. So where the relationship between scattered field and the permittivity profile is nonlinear. So the nonlinear iterative approaches, there are in two ways it can be classified. There are deterministic approaches like contrast source inversion, conjugate gradient method, inexact Newton method, modified gradient method, distorted Born iterative method, and subspace optimization methods. And these comes under the deterministic non-iterative nonlinear approaches. And whereas the stochastic and heuristic approaches means there are genetic algorithm and colony optimization, simulated annealing, differential evolution, and particle swarm optimization. So these are the non-linear approaches. These are the iterative approaches. They give better result compared to linear approaches like Barn approximation method. Again, the main problem here with these conventional methods are the computational cost. As I said, these are iterative method, very high computational cost is there, and hence they are not useful for the real-time applications. So because of this, the deep learning approaches are used. As we know, in the deep learning approaches, only the training will take a lot of time, but the testing will happens in no times. Okay. So artificial neural network based methods are used for inverse in various papers. It is addressed. So direct inversion from scattered field using convolution neural network is also tested. So directly from the scattered field, they try to find the permittivity profile, but the problem that result is not that much accurate directly from the scattered field. So what they use this CNN convolution neural network is used for post processing the initial reconstruction by some of the algorithms like BAP propagation algorithm, discretized filterized back projection applied to the scattered field, and subspace based variation Barn iterative method. So some of the conventional methods, with that they find the initial solution, and then they use the CNN as a post processing. And also in one of the paper, the output of CNN is also iteratively they refined it. After finding the result from the CNN, convolution neural network, they refined it iteratively to improve the result. So these are some of the work they have done. But in in almost all the paper, the UNet architecture, UNet is one of the convolution neural network architecture is used in almost all the papers. So with the advantage of deep learning, so we can have a objective that enhance the quality of image reconstruction, reduce computational time, and improve these are the advantages of the deep learning. So our objective, okay. So we can embed this deep learning into inverse problem. Okay. So there are two types of objects are there: dielectric objects and PEC objects, perfect electric conductor objects, and mixed objects. So we can have a first problem like embedding deep learning in inverse problem to reconstruct dielectric objects. So we know that a dielectric is an insulating material that interacts with electromagnetic fields. Its dielectric properties, primarily its dielectric constant, determine how microwave signals are absorbed or reflected and transmitted. So allowing the imaging system to detect the difference between the tissues or objects based on these properties. For example, again, as a sir said, water-rich or cancerous tissues typically have different dielectric properties than healthier tissues, which creates contrast in the resulting microwave image. So glass, plastic, mica, porcelains, and concrete biological tissues, distilled water, transformer, oil, etc. These are the example for the dielectric objects. So the application of deep learning to address electromagnetic inverse scattering problems is in the budding stage. It is in the early stage, and only few works are reported in the literature. Okay, so we can have an objective like developing a novel approach combining the conventional algorithm like distorted Barn iterative method or any other method which is not used in the literature with the deep learning to improve the reconstruction of dielectric objects. So in the conventional method, they take more time as they are iterative, and also the result, because of local minimum problem, accuracy is also not good. The reconstruction quality is also not good. So we can develop a novel approach combining the conventional algorithm, which were not used in the earlier paper. So like distorted Barn iterative method or any other method with the deep learning to improve the reconstruction of dielectric objects. So this is one of the objective we can keep. And second one is reconstruction of perfectly electric conductor objects. So the detection of PEC is essential in various applications like concealed weapon detection, localization of metallic contaminants in food products, and landmine detection. So detection of conductor is important. So for this, only as the sir told here, all the waves are reflected, and only we are concerning about the shape of the object in case of PEC. So linear sampling method is one of the qualitative imaging. This is not quantitative. This is a qualitative imaging procedure used for the shape reconstruction of dielectric as well as metallic targets. In linear sampling method, there is a advantage. There is a limitation that is there is a limitation or drawback that the quality of output depends on frequency of operation and the choice of regularization parameter. Okay, so based on the frequency, the reconstruction quality also varies, and the choice regulation parameter if you vary, then also the reconstruction quality varies in the linear sampling method. So this is already studied in this paper. So what we thought is we can have a second objective of integrating deep learning with the linear sampling method to reconstruct the geometrical properties of perfect electric conductors. And also, so we said there are some limitations of LSM with respect to frequency and regulation parameter. So that also we can address using deep learning. Okay, we can address the issues of LSM regarding regulation parameter and operating frequency. So similarly, for other methods, in the conventional method, if there are any limitations, that also we can take as a research problem and we can solve it. And the third one is reconstruction of mixed boundary objects. The many real-world objects have mixed boundaries consisting of both dielectric and conductive materials like coated metal cylinders, human body with implants, and reinforced composite, that is RCC, reinforced composites, and printed circuit boards, etc., where plastic and conductors both will be there, dielectric and PEC objects. So accurate reconstruction of these mixed boundary objects is crucial for practical applications. So deep learning is not yet applied for reconstruction of mixed boundary objects. So we can use linear sampling method for this reconstruction of mixed boundary objects along with the deep learning. And another characteristics of linear sampling method is it behaves differently for dielectric and PEC objects. At low frequencies, it can detect PEC objects, but not dielectrics. At low frequency, it can detect only PEC. It cannot detect dielectrics. So this is like the limitations or the characteristics of the LSM. Next, we can have a next objective like introducing a deep learning based linear sampling method to reconstruction mixed boundary objects. And we can address the limitations of traditional LSM for mixed boundary objects. The LSM has a problems with LSM for PEC also. Like for a different frequency, its reconstruction quality is different. In the previous slide, we can see. And also with regulation parameter, it varies. For mixed boundary, its limitation, the limitation of LSM is that at low frequency, it can detect only PEC, but not dielectric. So, and after the reconstruction, as the domain of investigation has both dielectric and PEC, so we can also do the classification of mixed boundary objects after reconstruction. So normally in a microwave imaging papers, they will do the reconstruction part and classification of mixed boundary objects. Also, we can do that. Okay. So the next we can have the applying deep learning to off-space problem. In the off-space problem, so GPR is a non-invasive geophysical technique used for subsurface imaging. The major conventional methods for GPR imaging are radargram and tomographic approaches. In the radargram, the radar pulse are emitted to the ground and the reflected signals are captured And according to that, they will try to study the buried objects. In tomographic approaches, electromagnetic waves are emitted, and from the scattered field, the reflected scattered field, they try to estimate the buried objects. So again, these two conventional methods are again they limited by their accuracy and their high computational cost. So we can apply deep learning along with conventional method to reconstruct the subsurface data. So in the half-space problem, so there are two imaging configurations are there. Bistatic imaging configuration and multistatic imaging configuration. In bistatic, only two antennas are used. One acts as a transmitter, another acts as a receiver. And whereas in multistatic, the multiple antennas are used. So in the bistatic, it is simple, but accuracy is less. Whereas in multistatic, it is more antennas, hardware complexity is more, but reconstruction quality is little bit better. So you can have some research problem like having less number of antennas, like 3 or 4. You can study the another configurations instead of having an in number of antennas. So 3-4 antennas with less number of antennas, can we reconstruct good quality? So develop a novel imaging configuration to improve the tomographic reconstruction of buried targets. So after seeing these problems, so I was telling that most of the time use deep learning. So the term deep learning is so now I want to discuss little bit about the deep learning for another 5 to 6 slides. The term deep learning is kind because in the neural networks there is the input layer, output layer, and the hidden layers. So if more hidden layers are there, then it is called as deep learning. The term deep learning is kind because the neural networks have various hidden layers. Okay. So in the past few decades, deep learning has proved to be very powerful tool because of its ability to handle large amounts of data. There are various types of deep learning networks are there. The various are there. Out of that, convolution neural network is most popularly used. So convolution neural network is one of the type of deep learning network. So in convolution neural network, it is a type of deep learning algorithm used in image recognition and processing that is specifically designed to process pixel data. It uses a special technique called as convolution. So in 1980s only the CNNs were introduced to do the handwritten digit recognition and found applications mainly in the postal code reading. Due to the lack of large data sets and sufficient computational resources at that time, their adaptation remained restricted and delayed their broader impact on the machine learning. So in the CNN also, there are various models are there, LeNet, AlexNet, ResNet, GoogleNet, and various are there. So UNet is one of the types of CNN models. Okay. So UNet is one of the types of CNN, and CNN is the type of deep learning. Okay. So the UNet evolved from traditional CNNs, was first introduced in 2015 for biomedical image processing, where the task involves not only detecting the presence of disease, but also accurately localizing the affected regions. So UNet is dedicated to solving this problem. The reason it is able to localize and distinguish borders is by doing classification on every pixel. Okay, normally the CNN we said that whether there is a object is done or not, like that it is there. But now it has to work on pixel by pixel. Okay, so it is utilized for task that the prediction has the same spatial dimension as the input. The UNet architecture consists of an encoder and decoder subnetworks. So the architecture it looks like this. It is in the U shape. This part is known as contracting path and also known as encoder part, and this part is known as the decoder part. Okay, so in the microwave imaging, the softmax layer at the output in the original UNet is removed and the regression layer is replaced. So you cannot use the UNet architecture directly. So this one small modification you have to do to use the UNet architecture in the microwave imaging. Okay. So this unit architecture, the basic building blocks are convolution layer, ReLU, and max pooling layer, transport convolution layer, and one by one convolution. So in the microwave imaging paper, in the unit architecture means normally they will mention only this. So the details of this will not be mentioned much. So in the convolution is the core operation, the convolution neural network, where a small matrix of learnable weights called filter slides over the input data and performs element-wise multiplication and summation. So this linear operation is applied repeatedly across the input to produce a feature map, which highlights the present and the strength of specific features such as edges or textures in the images. Okay. So here, if the input to the convolution is n in cross channels, then the output will be of n out cross number of filters, where n out is given by this expression. Okay. So in the next slide, you can see that one example is there. Okay, so this is a 5 by 5 image. This is the kernel or a filter. So here what happens here, each this 3 by 3 image, first it will overlaps here. Okay, so they each value by value it is multiplied and added. Then that feature first value is calculated like that. So here I have shown that here this 1 into 2 plus 2 into 4 plus 3 into 9, like that it is calculated. Similarly, next value, so this will slide. That is called as a stride. Okay. So if stride is 1, then only one position it moves to the right. So it overlaps with this part. So the kernel overlaps with 491, 144, 129. Okay. So and the corresponding values are multiplied with the kernel and added. So next value it will be 66. And again it is moved one position and like that. So and also it is moved vertically down also. So when it moves vertically down, 214, 112, 735 overlaps with this, they multiply and add, and that value will comes here. Okay. So here the no padding is done. If you do the padding, the zeros are padded completely in all the 4 directions. So like this, the convolution operation happens. So here the illustration is for the width padding, and also if the stride is more. If the stride is more, then the feature, the output is reduced. If the more stride means jump. So here stride is 2 means after calculating this, then it will, instead of moving one position to the right, it moves 2 position to the right here. Okay. So the ReLU, the rectified linear unit, is the most commonly used activation functions. There are other activation functions like tan hyperbolic, sigmoid, other activation functions are there, but ReLU is used in the deep learning because of its computational inexpensive, and it is allowed the model to train and run faster. It also allows the model to effectively capture non-linearity and complex interaction in the data. And the max pooling layer, it is used to reduce the size of the feature map. Okay, so max pooling, not only there is average pooling is also there. Again, the average pooling means again computational time is more. Okay. So here, if the kernel size is 2 by 2, this is the input. So 2 by 2 means it will take 4 pixels. Out of that, the maximum value it will select. Okay. Next, if the stride is 2, if the stride is 2 means it will position, it will skip, it will move to the right by 2 places. Okay. Next, 7364 maximum is 7. That value comes here. So like this, the max pooling is used to select the features. And this transpose convolution is used to increase the size. As we can see here, in the unit architecture, here the dimensions of the input reduces. Here 32 by 32, like it is an encoder path. In the encoder, the dimension reduces. And during decoder, this dimension increases. Okay. Here is the same dimension increases. So for this, transpose convolution is used. So transpose convolution is used. So here also, this particular pixel is multiplied with all the kernel values and they are placed here. And next, this pixel is multiplied with all the values and it is placed here if there is stride is 2. then the overlapping portions are added. In the next slide, you can see this example. The input is 0, 1, 2, 3. The kernel is also 0, 1, 2, 3. So what happens? This 0 is multiplied with the kernel values that comes here. Then this 1 is multiplied with this kernel value. With straight 1 here it is mentioned. And 2 multiply and they placed. So then all the 4 intermediate these things, they are added. And the overall, you can see this. So input is 2 by 2. Now the output is 3 by 3. Okay. So in contrast to the regular convolution that reduces the input elements via the kernel, the transport convolution, the broadcast or enhances the input via the kernel, thereby producing output that is larger than the input. So finally, the one-by-one convolution layer is important in various CNN architecture like GoogleNet, ResNet, and SqueezeNet. So here it is used to reduce the number of channels. So it is actually 64 by 64 and 192. But here we have used a kernel of 1 by 1 into 192. So actually what it will do, here the first element, all the 192 value here multiplied and added. One single value we will get, that is placed here. Next, second value in the first row, all 192 values are multiplied here and placed here. Like that, vertically also it is done. So finally we will get 64 by 64. So to reduce the number of channels, 64 by 64 into 192 is converted to 64 by 64. So these are the 5 operations are very important in the CNN architecture. Okay, so after building the CNN architecture or unit architecture, you have to train. So normally during training, so we will use mean square error as a loss function, and the parameters are tuned using the Adam optimizer. The other optimizers are also used, but most frequently Adam optimizers are used with a small learning rate like 0.001. And the training data set may comprise of synthetic data like MNIST digits and letters, rectangular and circular objects. You can create the training data, and then it is trained for fixed number of epochs with appropriate batch size and the iteration. So, and the diagram looks like this. Find the scattered field from the conventional algorithm. Okay, so from that, the initial value we will obtain from Born approximation or some other method, conventional method, and the actual label. So the actual label and the estimate are used to train the unit, and from that you will get the trained unit. So unit is trained using actual ground truth images or original profile as a label, and the estimate obtained from the conventional method is as a training input, and this is a training label. Okay. So we'll get the trained unit. So from in the MATLAB, so this is at various levels, what is the input size and output size. So based on this equation, you can verify this. So it starts from 32 by 32 by 1. It goes on, increases like this, and again transpose convolution. So it goes, finally the output will be 32 by 32 by 32 by 1. So, and also the number of learnable parameters we can see. So there is a formula, filter height, filter width, and number of channels, input channels, number of output channels, and this is the expression to find the number of learnable parameters. So in this example, so finally there are 45 layers are there, and the total learnable parameters, it turns out to be 77,33,121 learnable parameters are there. So, and these are some of the results. So this is the first one is a dielectric object, so created from the MNIST data set. And this is the result from the distorted bar iterative method up to 10th iteration. And this result is obtained from the deep learning algorithm. So here it is known as Astrea profile. In the microwave imaging, this profile is known as Astrea profile. So here this is a heterogeneous Astrea profile, because the circular disk and two circular objects all have a different permittivity values. So for this, the reconstructed result from the DBIM is it is identifying the object, but its shapes are not correct. Whereas through deep learning, we can have a good reconstruction quality. And this is one of the layered profile objects. So from the DBM, the reconstruction was not that much good. And from the deep learning, you have some reasonably good result. And this one is the original profile from the experimental data set. So using synthetic data, what we have created, from that we will train. But finally, to publish in a paper, if we want to test in experimental data, so there is a standard data set given by the Institute of Fresnel. Okay, so in that, this is the two dielectric objects having different radius and permittivity value. So for this also we have tested, and from the dielectric, from the DBM, the reconstruction result was like this, and from the deep learning, the result is like this. And this one is for mixed boundary objects. So the LO object, we will say LO shaped object. So L-shaped dielectric and PEC object is there. So from the linear sampling method, the reconstruction quality, it detects the object, but the shape and size it will not correctly detect. So whereas the deep learning, for the mixed boundary object, it is relatively okay. It gives a reasonably good results. So as I said, we can, after for the mixed boundary objects, after the reconstruction, we can also classify. So here in this original profile, 3 dielectric objects are there, 1 PEC objects. So here what we have used is the limitations of LSM we have used. So the LSM at low frequency detects only PEC. So it detects only PEC objects. And at higher frequency, after applying to deep learning, the reconstructed result is like this. So here all our objects are detected. The objects detected at low frequency and objects detected high frequency through CNN is PEC. So that is mentioned by the red, indicated by the red color border. Okay. So in the MATLAB console, you can see the total number of objects are 4 and the number of dielectric objects 3. The total number of PEC objects is 1. So like this, we can classify the objects also. So after the reconstruction, so we want to quantify the efficiency of the reconstructed results. So now for that, normally mean square error, structural similarity index measure, and misclassified pixels error, these parameters are used. So structural similar, the mean square error, you know that the original profile minus reconstructed profile, they are subtracted, squared, and added all the values, and the square root is taken. So as per this formula, so mean square error is calculated. And also SSIM. For SSIM, it is fine. No need to worry about this equation. In MATLAB, there is an inbuilt function. So this SSIM, structural similarity index measure. So if reconstruction and original image both are same, then its value is 1. If 100% mismatch is there, then it gives the value 0. So the another method, for qualitative reconstruction methods, so you can map the reconstruction, because here only we are worried about the shape, not the values. So the reconstructed values you can map to binary images based on some threshold. That threshold can be calculated based on the minimum and maximum value of that particular image. So after converting to binary image, you can subtract, find the absolute value, and divide by the total number of pixels. Because here the error may happen, the misclassified pixel, it may be inside the objects or outside the object also. It can be anything. Okay. So this can also be used for that. So future research directions. So first, the normally to have the microwave imaging applicable for the real time, it should be extended to 3D extension. But most of the work, they are limited to 2-dimension. So extending the microwave imaging to 3D extension is a good research problems, and improving the limitations of conventional algorithms. Okay. So as I said, in the LSM, some limitations are there. It is a qualitative imaging method, so it can be converted to quantitative also. So improve the limitations of conventional algorithms, and the most of the objects studied are isotropic. For anisotropic scatterers also it can be applied, and the other integrations, it can be merged with other modalities like MRI and CT images. So the image fusion techniques we can use, and the advanced deep learning architecture. So if the deep learning with UNIT is already applied, means other deep learning architectures which are developed can be used for microimaging, and the results can be again improved. And also the multi-frequency plus deep learning. So not only single frequency, with multiple frequencies and deep learning can be used for conventional algorithms. And we can develop the hybrid algorithms, conventional algorithms plus deep learning. So conventional algorithms which are not used can be combined with the deep learning for the further new algorithm. Okay. So these are some of the references. Thank you. So thank you, sir.
Brahmareddy sir, your voice is not coming, sir. Sir, your speaker is in mute position, sir. Brahmareddy sir, your voice is not coming. Same problem, sir. Still voice is not coming again. So there is again problem arisen, sir, in your system. Voice is not coming. Sir, your voice is not coming. With your kind permission, we will ask any other persons to ask any questions, sir. And you can your questions you can directly ask through phone, sir. Okay, sir. Okay. So other participants, any questions, sir?
The questions will be arrived in the bottom question and answer this icon, but no question is there till now, sir.
Okay, thank you. Then, okay, now I am requesting Sri B. Srikanth, Honorary Secretary, to cast vote of thanks and followed by national anthem. Thank you. Srikanth garu.
Okay, sir. Thank you, sir. Thank you. Respected dignitaries, esteemed speakers, faculty members, professionals, students, and dear participant. As we come to conclusion of this webinar on microwave imaging and application, it is my proud privilege to propose the vote of thanks. First and foremost, I express my sincere gratitude to our distinguished speakers and panelists for sharing their invaluable expertise, insightful discussions, and rich research experience. Their contributions have greatly enriched the and academic values of this program. I extend my heartfelt thanks to the chairman, moderator, and organizing committee members for their guidance, coordination, and tireless efforts in successful planning and executing this webinar. I also gratefully acknowledge the support and encouragement extended by the Electronics and Telecommunication Engineering Division Board and the Institution of Engineers India for approving and supporting this CPD program. My sincere appreciation goes to all the participants, including faculty members, researchers, professionals, and students, whose active participation and engagement made this event lively and meaningful. Finally, I thank the organizing team and technical support staff for their behind-the-scenes efforts, without which this program would not have been possible. With this, I once again thank everyone for their valuable time and participation, and I hope this webinar has been a rewarding learning experience for all. Thank you and have a pleasant day.
Now, national anthems are now.
So,
नायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उज्ज्वल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगल नायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you all of you, sir. Thank you. With this program is concluded. Thank you.
Thanks.
Thank you, sir.
thank you, sir.
One announcement for the participants. Our e-certification link is open till tomorrow midnight. Those who want to collect their e-certificate, kindly log into the e-certification link and kindly proceed for the e-certificate. It will be delivered by 27th. Thank you. Thank you, sir.
Thank you, sir.